Okay, so let's continue our look at Laplace transforms. And today we're going to see kind of what the advantage of using Laplace transform is. Okay, this all goes back to a famous English mathematician, electrical engineer, and sort of like a pioneer in the early stages of telecommunications. He was really involved with cable and telegraph. He worked out a lot of stuff. I think he invented the coaxial cable. And so Laplace transforms had been invented by Laplace, of course, in the early 19th century, and he was looking at some problems in probability. And Heaviside was among a group of mathematicians in the later part of the 19th century who started seeing the advantages of using Laplace transforms to solve differential equations. And so the big contribution is that you can handle discontinuous forcing functions with Laplace transforms. And these kind of discontinuous forcing functions occur a lot in engineering problems. And you might think, well, isn't the discontinuity going to screw up the differential equation? And the answer is no, because when you solve an ODE, you're integrating, right? And integrating will smooth over those discontinuous points because the value of a function at a single point doesn't affect an integral. Okay, so what Heaviside realized was that to write a piecewise continuous function as a single expression, you need what's now known as the Heaviside step function. So at t equals 0, it's just defined to be 0 if t is negative and 1 if t is positive. And in general, a unit step function at t equals c is defined to be 0 if t is less than c and 1 if t is greater than c. And we don't really care what happens at c. Okay. So in handling discontinuous functions, you can just write it as using these Heaviside step functions. So given an arbitrary piecewise continuous function with n jumps, and we assume it's continuous between the jumps, so in one there, that's a typical way that you have a piecewise defined function, right? You have an interval, and you have a different function on each interval. And so you just write it as a single expression where it starts off being f1 of t, and then at time t1, we replace f1 by f2. So all we've got to do is multiply the step function at t1 times f2 minus f1, right? Because at t1, that u becomes a 1. So you're adding f2 minus f1, you add that to f1, it changes to f2, etc. And you do that all the way down at the end for all the jumps. And so let's have a look at examples. Here's a piecewise function. So it's equal to t for t between 0 and 1, and then it's turned off. It's 0 afterwards. Okay, and so that's going to be t, because that's our starting function. And then at 1, we want it to go to 0, so we just subtract t at 1. So the way to do that is you do minus ut minus 1 times t. And you just check it out that when t is less than 1, u is 0, so you just get t. And when t is greater than 1, you've got t minus t. Okay. The second problem there. So let's say you're supposed to be, you've got some tank, it's a mixing problem, you've got a tank of pure water, say, of 10, and you're going to add salt in it, and you want, you start off with the first 4 minutes, you're putting in 1 pound of salt per gallon, it's coming in at a gallon per minute, and then the boss tells you, oh no, you've got to be doing it 2 pounds per minute. So what you do is maybe for the next minute, you throw in 6 pounds. So you have 6, mix it up well, you have 6 pounds for that minute. And so at the end of 5 minutes, that gets you up to 10 pounds that you've added in. And then afterwards, you go at the rate of 2 pounds per minute. And that's pretty easy, right? So you start off with 1, and then at time 4, you want to put in 6. So you multiply the step function by 6 minus 1, right? 6 is what you want to be. You subtract what it was before. And then at 5, you want it to go to 2. So you've got to subtract 6. And after you do all the arithmetic, you see you got it right there. Okay, the third one is like some sort of sawtooth function. So there's lots of different ways you can define that. There are different types of sawtooth functions. But so this one here is basically it's equal to 1 minus t on that unit, first unit 1, and then you just now make it into periodic function. And so on the interval n to n plus 1, it's n plus 1 minus t. Okay, so this is useful. You know, you might have some kind of electrical thing going on here, or this could model a drug, right? So the idea is you inject someone with a drug every time period, and it starts off at that high level, and then over time, the amount of drug in the body goes away. And so we're just assuming that it goes away linearly. And so you'd get a sawtooth function for that. You can also use it for continuous functions that are still defined piecewise. For example, let's have a look at the absolute value of sine t. That could be a forcing function. That's one you could use in electrical engineering, right? Because you go from AC, which is kind of nice sine wave, and you rectify it to be DC, so always going to be positive, so change it to absolute value sign, right? So you go through, and again, you can write it as some kind of series sum. So it's, you start out at sine t, and then at pi, you want it to be minus sine t, right? So you take the minus sine t and you subtract the sine t. And then at 2 pi, you take the sine t, and now you want it to be sine t. And then at 3 pi, you want it to be minus sine t. So you go through and you do the arithmetic, and we can write it as sine t minus 2 times the step function times sine t, right? So we do it at each pi, 2 pi, and we're alternating sum. And you remember that, well, sine is periodic, and so it's, if you replace t by t minus pi, that's the same thing as minus sine. And t minus 2 pi is the same as sine. T minus 3 pi is the same as minus sine. And so when you do that, you kind of you put the sine in sync with the step function. And there's a series there that we use. Okay, so your first module question is, write as a single expression that there. Okay, and so the big thing is, of course, we have to know how we're going to do the Laplace transform of that. And so the Laplace transform of the step function is just e to the minus cs divided by s. And so for the first time, we've introduced an exponential in the Laplace transform land. Okay, and then the Laplace transform of the step function times f of t minus c is e to the minus cs times the Laplace transform of that f. And you can, this is actually the hard bit about Laplace transform, is this shift you get when you make that jump. And so you could either have f of t minus c, or you could have f of t, right? And so the Laplace transform of the step function times f of t is e to the minus cs times g of s, where g of s is the Laplace transform of the shifted function f. And the proof is pretty straightforward, right? Because if you take the Laplace transform of the step function times any function, right, then you go to the definition. The definition goes from 0 to infinity, but the step function is 0 between 0 and c. So we turn it into the integral between c and infinity. Okay? And then we make a change of variable. So we make tau equal t minus c, right? And then when t t is c, tau is 0. When t is infinity, tau is infinity. So it changes the integral from to 0 to infinity. And then we get an e to the minus s times tau plus c. It's just by the change of variable, times f of tau. And now you can pull out the e to the minus cs because there's no tau in that. It's a constant as regards integration. And that integral there is just then the Laplace transform of f. Okay, and so that proves point 2 of the theorem. Point 1 is just a special case of that, right? When the function f is a constant. And then for part 3, you just do a change of variable. So when you do t minus c, you go to s, but if you go t plus s, you go to whatever. So it just makes the formulas work. Just go through that. Okay, so let's look at the examples that we've done before, right? So we had t minus ut minus 1 times t. Okay, so the Laplace transform of t is 1 over s squared minus, well, since we've got a step function, we're going to multiply by e to the minus s times g of s, right, where capital G of s, where capital GS is the Laplace transform of the f evaluated at t plus 1. And t plus 1, of course, is just f of t plus 1, of course, is just t plus 1 because f of t is t. It's just the identity function. So the Laplace transform is 1 on s squared plus s. Okay, and so there's your Laplace transform there. So you can kind of have a little sense what the Laplace transform actually is, right? I said it was kind of like a formal thing. So you never evaluate in anything for S. So what the Laplace transform is, it's like a formal function. And so by a formal function, I just mean it's a function which just has information encoded in its representation. So the numerator encodes what functions are involved in the solution. The numerator tells you what the coefficients of those functions are, and exponentials tell you that you've got something happening at that point. It's kind of a way to put all the information of what's happening at a discontinuity. Our h of t, which was, remember, 1 plus 5 times the step function of 4 minus 4 times the step function of 5. That's fairly straightforward because we don't have to worry about the shift because we're dealing with constants. For the sawtooth function, the Laplace transform, well, we Laplace transform 1 minus t to be 1 over s minus 1 over s squared. And the Laplace transform of the series is really simple because it just turns out to be constants. A little bit sneakier is, well, you can see why I shifted the sine function to be in sync with the step function, because then we can just write down straight away what the Laplace transform is. And so we've got sines, so it's 1 over s squared plus 1, and then we just have the exponentials at each sort of point of change of definition of the piecewise function. And for your second module question, I'd like you to find the Laplace transform of the function that we found before. Okay, so I'll have a pause now and go to a new video and where we'll actually go through some examples.